Hello friends, today I am going to show something related to 1D wave equation. Actually, it's beneficial for CFD coding. So let me see 1D wave equation. Actually, in the last, I am going to show you that uh, how the wave is behaving by using the upwinding and central differencing and upwind differencing. So this is the 1D wave equation, del u by del t, c del u by del x is equal to 0. So we can discretize del u by del t in a forward in time. And if c is positive, then we have to use backward in space. I have to use backward in space for upwinding. If we rearrange this, then then we will get like the equation like this. And this is c delta t by delta x is current called as current number. And if we will go through one Nyman stability analysis, then we will get that c delta t by delta x would be less than 1. Okay. So okay, from discretized equation, if we want to get the original 1D wave equation, then we have to use Taylor series, and instead of u I n plus 1, we can write this whole thing that is in bracket. Okay. U I n del u by del t I n del t del square u by del t square I n. I n, what is mean by I n? Substitute means that at a place I n at a time step n, this derivative should be at x node I or and at a time n. So del t square by 2 factorial, del u q by del t q, del t q by 3 factorial, dash 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 dash, and minus u I n, that is here written here, divided by delta t, and plus c, and I have again used the u I minus 1 Taylor series expansion. Okay. And after after rearranging the terms del u by del t, c del u by del x, you will get that minus del square u by del t square, del t by 2 factorial, del square u by del square u by del t square, delta t by 2 factorial, del square u by del x square, delta x by 2 factorial, plus order of delta t square plus order of delta x square. Okay. I have to replace this del square u. I have to convert del square u by del t square is a del square u by del x square. So I am using the original 1D wave equation. So we can write del square t u by del t square. We have to differentiate this 1D wave equation with respect to time. So you will get that del square u by del t square minus c del by del t del u by del x. And del by del t del u by del x, what you can write instead of del by del t del u by del x, you can write if you differentiate again this with respect to x, then we will get del square u by del x del t is equal to minus c del square u by del x square. So instead of del square u by del x del t, here we can put minus c del square u by del x square. So minus c will put to c square del square u by del x square, it will become. So I have written that c square del square u by del x square. So instead of this c square del square by del square u by del x square, and if we common that, if we will take common del square u by del x square, then we will get the terms related to coefficient related to del square u by del x square. So now we can see we supposed to solve the 1D wave equation, but in originally we are not solving the 1D wave equation. We are solving the in 1D wave equation we are thinking that no diffusion term, right? So but here we can see that diffusion term is present here, and when diffusion term will be 0 when delta t and delta x tending to 0, but delta x and delta t should be such that the delta x and delta t should be such that the one Nyman stability criteria should should follow. So okay, and this what if we use if we use the coding, if we do the program of this 1D variation, then we will see that the what is the u, actually u is the amplitude of the wave. Okay, u is the amplitude, not velocity. Velocity is the c is the velocity of the wave. U is a any function, anything which is having some amplitude like phi, anything. Okay, so amplitude of the wave. So amplitude of the wave will decrease with respect to time, because here we can see here the diffusion term is present in the equation. So amplitude of the wave, because of the diffusion term present here present in equation, the amplitude of the wave will decrease with respect to time and space. Now let me come to coding. That means let me come to uh, coding. So I have done the coding for 1D vacation and upwind. Okay. So this is the x span. This is the velocity of the wave. This is the delta x. This is the delta t. Okay, and this is the x coordinate. Okay, so this is the number of nodes in x direction, and this is the initialization. It here u2, u3, u4 and u5, the wave amplitude will be 0.5, and another places the wave is having zero amplitude, right? So this is the time. At a time, obviously these things will be at the time equal to 0, and there I am finding the current number, and this is the time step. I am using the time step to 200 time step, and this is the upwinding equation, that discretize upwinding equation, and all this I am using this all these things to record the video. Okay, so now we will run this code, and we will see that what is happening to the wave. Okay. Now you can see that amplitude is decreasing, right? It is going in x direction, and amplitude is decreasing. I click. Now at the last you will see that amplitude is very low. Actually, amplitude have been started from its initial amplitude was 0.5, but now its amplitude is 0.008. You can see here, 8 into 10 to the power minus 3. It have been decreased very in shorter time. Okay, now you have seen you have saw that the amplitude have been decreased. Okay, and here some error is coming. Okay, I will find out that. So now we will see that when we will use the central differencing, then what will happen? Just ui minus 1, here will be ui plus 1, ui minus 1, 0.5 multiply will be here, because del u by del x, we can write del u by del x ui plus 1, ui minus 1 divided by 2 delta x. So 0.5 will be here. Now we will run again this code. Okay, so just I have to n minus 1, and I have to use I have to boundary condition equal to u n equal to u n minus. No, now you will see that using the using. Okay, just a minute. Okay, okay. Now we will see that what will happen when we will use the central differencing. Wait a minute. What is? Now we'll run that again. This we have. I have used the central differencing, and we can see that the this is called actually dispersion error. I will tell you what is the dispersion error. Actually, okay, let's finish the first uh, animation. Let me run this again. You can see that the initially amplitude was 0.5 at the 3 node, but it is not actually uh, actually it is not giving the right answer, right? This is called as a dispersion error, and I will tell you what is the dispersion error. Okay, I have to use the pen. So actually the wave was like, I have given the amplitude of the wave at the 3 node, and other places it was 0, right? The wave should travel like this only, but in upwinding, the because of the central difference, because in upwinding, because of the diffusion present in the equation, the uh, the wave became like first this, like this, and now it traveling in this direction. After some time, we have saw that after some time the wave of amplitude was decreased, right? Amplitude of the wave was have been decreased. Now what is being in dispersion error? What is being in dispersion error? So we know that this wave, this wave sorry, this we can write Fourier from Fourier decomposition. It can be summation of the multiple frequency. Like one frequency is like this, one frequency is like this, another frequency is like this, and another frequency is like this, and another frequency is like this, and summation of all these frequencies will be summation of all these frequency will be the this square wave, right? So if we'll add this frequency, then we will get the square wave. Lekin problem is the problem is that the all frequency is not traveling at the same speed. In central differencing, all frequency is not traveling in a same speed. So one frequency is traveling like that, one frequency is here, and another frequency is here, and another frequency is here. So we will add the, if we will add, then here we will not get 0, he will either here also not we will get it, and here we will add that if we will add, then this square wave also we will not get. Okay, so this is the problem with central differencing. And what happened in central differencing? The diffusion term will not come. That means the derivative of derivative is del square u by del x square will not come. Actually, of instead of del square u by del x square, it will come del q u by del x cube, del q u by del x cube. So here will be del q by del x cube. Okay, so here will be del q by del x cube. So this is all about 1D wave equation, and why at the last I'm telling you why we have done analysis on 1D wave equation. Actually, in Navier equation, the convective term present there. So convective term, and in this equation also convective term present here. So and stability and other things is not related to diffusion term present in equation. We will do 0 to diffusion. We will give the 0 weightage to diffusion equation, and then we will do analysis using the using one dimensional equation. And if mesh is Cartesian, then whatever we will doing analysis on 1D, it will same apply to 3D. So it's just so simple about why we use upwinding, why we not use central differencing, and if we use the upwinding, the what is the problem with upwinding, and what is the problem with central differencing. So another thing is that we can use the central differencing. Here also we can use the central differencing, but the problem is that we have to use the Peclet number should be less than, the Peclet number should be less than 2. And what is the Peclet number? Actually, it's a grid Reynolds number. So grid Reynolds number should be less than 2, and we will look this all these things in another video. Thank you.